What's up, people? It's good to be back. I feel like it's been a long time since I've made a video. So, we looked at a situation today with a hanging 2x4 and what it meant for it to be in equilibrium. So, well, we expand upon that in these slides. Okay? So we know so far that for one thing, equilibrium means, you ought to know this, I sure hope you do, that's what it means. It means the net force acting on an object or system is zero. It doesn't mean there are no forces, it means that the sum of all of them is nothing. Now, yeah, so that's, I guess, what we would say. We would say that for an object or system in equilibrium, that is true. All right, but when we talk about forces, what we do is, and I haven't really said this to tell you the truth, we treat all masses as what we call a point mass. All right, so a force that acts on an elephant, elephant trunk. Oh, that's a woolly mammoth. Sorry, woolly mammoth. Oh boy, their tails, sure. Woolly mammoth. A force that acts on a woolly mammoth. We treat the whole woolly mammoth as that, a point. All right, a point mass. And what we do is say that that point mass represents the object's what we call center of mass. All right, so forget about irregular shapes of things. Let's pretend that forces all act on what we call the center of mass. And what that lets us do is neglect a whole range of situations. All right, because let's take a simpler case, like I suppose our hanging 2x4. If we have a 2x4 hanging from a string, there's a tension force like that, and we apply a force not at its center of mass. Notice the tension force here acts right at the center of mass of that 2x4. But if I apply a force here, a thing that, this 2x4 might not accelerate across the room, but it will still rotate. All right, so some forces, well, lots of forces that don't act on object centers of mass can make things rotate. All right, and the tendency of a force to cause something to rotate is called torque. All right, now, how do you quantify torque? All right, well, we can look at cases like this. So this is a hinge here, and attached to the wall, assume, and this is like just a rod that's hinged at the end here that can rotate. All right. So the question is, which of these forces causes the most torque? Which of these forces would have the easiest time rotating this this hinged rod? Well, it's this one. All right. Well, now, if we apply different forces at the same place, which one would have the easiest time making this hinged rod rotate? Well, it'd be this one. Now, in this case, which force causes the most torque? Well, so the question is, should we push like this, where we're pushing, perpendicular to the rod, or, well, this one isn't going to do anything. If we pull on the rod, there's no way we make it rotate. This one could make it rotate, but this one will, notice, same force in every case. It's supposed to be that long. Same force in every case, but the angle that we apply the force at makes a difference, right? This says up here that the distance that the force is applied relative to the, what we call the axis of rotation, that distance matters. This one says that the size of the force matters. And this one says that the angle that that force is applied at matters. Those are three things that control how much torque a force can create. All right? Come on. Go. So, oh yeah, we just said this, that the torque a force can create depends on the following factors. Well, one, strength of force. location of, I'll call it application. And 3, I'm going to call it direction of force. Okay? So we get a case like this. Here's our force F that can and will make this hinged rod rotate. And the deal is that that whole force F does not make the rod rotate, but that component does. Okay? I'll call that F perpendicular. All right, so F perpendicular is responsible for the torque. All right? Now, yeah, torque is called a cross product. First time we hear that. You might have heard about dot products in math. Something about a dot product. Well, torque is called a cross product. There's things you can do with vectors. Right? We can add vectors. Here's a tip-to-tail addition of 2 vectors to get a result. Right? We can do, well, let's see. Here is what we call a scalar multiplication. This says if you have a vector like A that goes that way, and you multiply it by a scalar, you get a different vector. So this could be A, that could be F, you know, and the factor by which F is bigger in this case is a factor of M. So you can add vectors. You can multiply vectors by scalars to get other vectors. You can also take what's called the cross product of vectors. All right, and by definition, yeah, now, there's a couple of forces, or sorry, a couple of vectors we need. And this one vector here is called R. That vector that starts here and ends here is called R. All right, R by definition, yeah, we say that torque, and okay, the variable we use for torque is this, it's called a tau, capital tau. All right, now torque is a vector, and we say torque is R cross F, not R times F. We say literally R cross F. I mean, real physics types say that. So by definition, here's how you find the magnitude of the cross product of 2 vectors. You take the magnitude of the first vector, the magnitude of the second vector, and the sine of the angle between them. All right, now, if you notice, yeah, okay, there's F. F is the force. Now, yeah, this vector R. Vector R, by definition, goes from what we call the axis of rotation, the place that the rotatable object could rotate about. R goes from there to what we call the point of action or point of application of the force. So that's why we talk about this location of application, where the force acts. So notice, if the magnitude of the torque is R F sine theta, right? This is really saying that torque is R times F perpendicular, right? F sine theta is F perpendicular. And again, that's why we ask this question. Which part of force F actually is responsible for the torque? Well, the perpendicular component of F. Well, perpendicular to what? Perpendicular to R. All right? Notice, if we want this to be the biggest it can possibly be, we want the biggest value of a sine function, biggest value is 1. Well, that's true when the angle is 90. Right? If this force F up here points completely perpendicular to R, yeah, it's going to have the easiest time rotating that rod. The smallest possible value this can be, again, the smallest possible value of a sine function is 0 if the angle is 0. Right? So if F pulls this way, it doesn't make that thing spin at all or rotate at all. So we're going to do, you know, the biggest challenge in problems, in torque problems that we solve is finding the perpendicular component of F. All right, notice also that since torque is RF sine theta, well, it's measured in meters times newtons. We typically call it Newton meters, actually. Sometimes in like truck ads, you'll hear foot-pounds or pound-feet of torque. Pound-feet is like the English, but we'll do it in Newton meters, okay? In trucks, right, they talk about how much torque it can produce, because for a truck, you really want the engine to be able to twist or rotate the drive shaft, and that rotation of the drive shaft can make the axles turn and turn the wheels even when you're pulling things that are really heavy. So the ability of a truck to make the drive shaft turn even under, well, even when it has to provide a huge force is a selling point. Okay? All right. Let's look at a case like this where, physical therapy, blah, blah, blah. We want to find the torque about the knee due to this weight. So here's a 10-kilogram mass this person's holding in different positions. So what we can identify in each case is the vector R. Hard for you to see. Let's try it in red. Any better? R goes from, I do axis of rotation like that. I'll put a place and say, there's where we're saying this thing rotates around, right? And the force, here's our force, right? F, or F, F, or F. So in each case, if, well, when theta is 0, and we do torque is R F perpendicular, well, that's nothing, because there is no component of that force that's perpendicular to R. Okay? If we look at this case, when theta is 30, or when that angle is 30, let's see. There's F. I'm going to draw F a little bigger. I'm going to draw F like this. There's F. Well, here's F perpendicular, same as this. There's F perpendicular. And there's 30, so that's going to be, when theta is 30, that's going to be torque is RF perpendicular, or RF sine 30. Let's see. We're given R is 40 centimeters, 0.4 meters, 100 newtons times the sine of 30, which is 0.5. 50 times 0.4, 20 Newton meters, right? Yeah. If theta is 60, well, it just turns into RF sine 60, which is, I don't know what it is. You can do the math. If theta is 90, right, the only thing that changes here is this is RF sine of 60 degrees. If theta is 90, right, here's the case where R looks like this. F is straight down, so the entire weight of this thing provides a torque. All right, so that's just going to be, again, RF perpendicular, which is just RF, or 0.4 meters, 100 newtons, 40 Newton meters. Okay? Okay, now, for basic torque problems, all right, first thing we can for sure do is, now we're going to look at torque problems where things, kind of like in this case, don't actually rotate. All right, we're going to look at an instant at a time like this and say, what if you were holding the mass there, where it's not actually rotating? Okay, so if we want an object not to rotate, what we sort of saw today with our hanging 2x4, hanging by a string, and we'll call that an axis of rotation. We said there could be a force here and a force here that could be smaller. Right, now notice, this one, I'll call it our green force, can provide a torque that would make the thing rotate this way. The blue force can provide a torque that can make the thing rotate that way. And so what we can do is come up with a positive direction for what, for a torque, or for a rotation at least. So we can write not only net force statements, we can write net torque statements. These always start with a free body diagram. All right, this we already know how to do, and nothing changes. You can still write a net force statement. All right, next thing we'll do, this will be the new thing, is that we write what we call a net torque statement. And this part we'll get some practice with, choosing our axis of rotations carefully. And you'll see when we get to this, but the typical problem involves writing both sets of these things. You typically will need both sets in a good problem. Yeah, so here's the dealie, right? That has to be true. If something, for an object that's not going to accelerate linearly, it's not going to accelerate in a straight line. Well, this has to be true for an object that's, or a system that won't rotate. Okay? And that's our new challenge, to write net torque statements. So here's an example. Blah, blah, blah. Okay, we want to find the normal force the fulcrum exerts on the rod and F. And F is a force that keeps this thing balanced. All right, here's a big deal. Everything weighs something. What we will always assume, and what really works, is to assume that weight forces always act at centers of mass of objects. Okay? So this is a 5-meter long rod, and we can say that there's a force here that we call mg. And this we know is 2.5 meters. This is a 5-meter long rod. All right, there's a force here, and that keeps this thing, because the rod is touching that fulcrum. And if there were no other forces, this thing would rotate that way, right? So what we do is we push with a force here that we're calling F, right? It says at its left end, to keep this rod balanced, or to keep it in equilibrium, in rotational and translational equilibrium. So let's find normal force and find F. Now, the only thing we know how to do so far is to do this. Let's start with it. Right? This says F plus mg equals n. The downward forces equal the upward force. Right? I skipped the step where I would say maybe n minus F minus mg equals 0. I just jumped right to that. Fair enough. Well, unknown, unsolvable by itself. So let's write a net torque statement. Now, as we said in the last slide, what you have to do here is choose your axis of rotation carefully. And here's what I mean by that. Because torque depends on how strong a force is and how far away from your chosen axis of rotation that force is applied. If we choose the axis of rotation carefully, we can make this 0, which makes the torque produced by that force 0. So if I choose here as an axis of rotation, force F exerts or provides 0 torque. It's like saying if you want to open a door, you can't pull on the hinge. Okay? And now I would say, well, let's see. Normal force produces a torque that would try to make the rod rotate that way. mg provides a torque that would try to make the rod rotate that way. And those directions of rotations are opposite, so let's call the positive direction that way. So if we write a net torque statement, we have a torque provided by mg that's in the positive rotational direction. Here's our positive rotational direction. And there's a torque provided by the normal force that acts or would try to make this thing rotate in what we call the negative rotational direction. Those are the only torques. Notice, this force F does not produce any torque because it acts at, again, this is a hypothetical axis. Sure, the thing actually rotates around the fulcrum, but we can choose any axis we want to analyze this system about. So I chose, on purpose, the end, the left end, because that lets me get rid of the torque produced by this force. There is none. So now I can say that these two torques, the torque produced by mg and the torque produced by n, have to be equal. So this is r mg times, well, the force itself, mg, and this is r to the normal force times the normal force itself. But now we only have one unknown. So we're looking for normal. That's going to be, let's see, r mg times mg divided by rn. Now, rmg is, again, here's rmg, 2.5 meters. mg is 120 newtons. Rn here is Rn, and that's 5 minus this 3.5, so that's 1.5 meters. Okay? So let's see, 2.5 times 120 divided by 1.5, 200. Now to find f, we can take this and plug it back in there and say f is n minus mg. N is 200, mg is 120, f is 80. What do you think? Good torque problem. Oh boy. Yeah, now, what you do for homework is this. You show me, you prove that if you choose a different axis of rotation, you can still get the same values of F and N. They have to be the same thing. There's only one combination of forces if they're applied at those locations. It's going to put this thing in both translational and rotational equilibrium. All right, you choose a different, what do you call it? A different axis of rotation. Okay, and it can be anywhere you want, but there are places that are, well, places that'll work and places that won't. Okay, so again, write your net force, write your net torque, but with a different axis of rotation than we used in our last example. Okay? Nice. All right, folks. See you tomorrow.